This is just a short little booklet then to finish off all the year 11 work. You can see at the top here, there's a little 5 where you can download this Microsoft Word document and then print it at home so you can fill it in for your own notes. We've already come across a little bit of this before. So we're looking at nuclear reactions, and one of these reactions happens in a nuclear power plant, which we covered when we looked at all our energy resources and ways of generating electricity. So we're going to look at two nuclear reactions, which is fission and fusion. These are not types of radiation, so don't get confused with alpha, beta, and gamma here. So the first one we're going to look at is nuclear fission. Notice how that is spelled. So it has two S's in it. The other reaction we're going to look at is fusion, which has one S in it. If you write this word in an exam, don't think the examiner is going to give you the benefit of the doubt. It will not get marked correctly for either of those two words. So fission and fusion. First one we're going to look at is nuclear fission. And this is the one that happens in nuclear power plants. Okay. It's sometimes referred to as splitting the atom, which is actually not quite right because the thing that splits is the nucleus. So here we have our nucleus. And for nuclear fission, it has to be a big nucleus. Now, uranium is at the end of the periodic table. It's one of the biggest nuclei that there is. And particularly uranium-235, which is an unusual isotope. It's not as common as the most common isotope of uranium, which is 238. Uranium-235 is the fuel that we use in nuclear power plants because it is easier to split in two. However, it won't just do it by itself. What we do to make it split in two is we make it absorb a neutron. Now, what that does is actually momentarily the nucleus absorbs that neutron, becomes uranium-236, which is very, very unstable, and then it splits in two. So we go from having a uranium-235 nucleus to having two smaller nuclei. Okay, so we split the nucleus. Now, the way it breaks in two changes each time. So it doesn't always have to produce barium and krypton. In the same way, if you drop a plate off a desk, it's not going to smash the same way each time. You're going to get different size bits each time you break it. Therefore, don't be surprised in an exam if you see different nuclei being produced than the ones in this diagram. However, we refer to these as being the daughter nuclei. Okay, so we have the parent nucleus in uranium-235, absorbs the neutron, that's what causes fission to happen, splits in two. We sometimes have little bits left over, so these neutrons come from that same process over here as well. So you can see that in this reaction, the uranium nucleus is split into two big bits, or daughter nuclei, and also three neutrons. It's not always three, sometimes it breaks apart and there might only be two neutrons produced. Now, as part of that, it releases a huge amount of energy, and we mean huge in comparison to, say, burning carbon, okay, combustion. So if you notice here, it says it is 10 million times larger. So if you burn a carbon nucleus or carbon atom and you split a uranium nucleus, you will get 10 million times as much energy from the nuclear reaction there. Now, we can write a little equation just to show what happens in this reaction. You will not be expected to learn this off. However, you could be expected to do this in an examination. Okay, so we need to fill in the blanks on this this equation. So all you do is you just make sure that the top and the bottom lines add up. So if you see in the top here, on the left hand side we have 235 plus 1, so that's 236. And just treat this as an equal sign. The arrow is equal to 89. Use a smaller pen here. Plus 3 neutrons. Mass number of a neutron is 1, but we've got 3 of them. 3 times 1 is just 3. And we then need to find out what the unknown is here. So that's just 236 minus 92 is on the other side. And it gives us that this has to be 144. Okay, and you can see if that's 144, both sides add up to 236. Meanwhile, we need to find the atomic number of the krypton here. If you look on the left-hand side, we have 92 protons essentially in that side. Over here, we have 56. Plus this, the neutrons don't count when you're looking at the atomic numbers. So working out that this has to be 36. Okay, so could be asked to fill in the blanks here. You do not have to memorize that equation. Okay, there's lots of actually different ways that this can split in two, like we say. So therefore, we don't expect you to learn off all the different reactions. But this releases a huge amount of energy. However, if just one nucleus undergoes fission and splits in two, you wouldn't even notice it, because on a global scale, rather than on an atomic level, on a big scale, it's still a small amount of energy, even though it's 10 million times bigger than combustion. So to do this and get an amount of energy we're going to notice on a large scale, we need to do a chain reaction. That's what the next video will look at.